Welcome back to Maths with Mrs. J. We're now ready to talk about integration of e to the x and various combinations involving e to the x. Remember, e is a very special number. It's an irrational number. It's a transcendental number. It's approximately 2.71, but it is impossible to give it exactly as a decimal. As a decimal, it is non-terminating and non-recurring. So the only way to write that number exactly is to write it as e. One of the very special features of e is the fact that the derivative of e to the x is e to the x. That kind of also makes integrating it nice and easy as well, funnily enough. So if the derivative of e to the x is e to the x, makes sense that the integral of e to the x will be e to the x plus our constant term. Similarly, if we have e to the kx, where k is just some constant, we know using the chain rule that we'd get e to the kx times that k. So if we're going back the other way, and we want the integral of e to the kx, it'll be e to the kx, but over k. We have to divide by that number. It's just a constant, all right? You could put 1 over k out the front if you prefer to write it that way. Similar situation here, if you have e raised to a linear function, chain rule dictates that when you differentiate that, you get e to that function multiplied by the derivative of that function. So this is going to be a similar situation to this here. We're going to get, so if we wanted the integral of e to the ax plus b, we're going to get e to the ax plus b, but we're going to get 1 over a times it. Doesn't matter, here you could have written 1 over k out the front. This here is very similar to what we were talking about in our previous video. This is another chain rule in reverse situation, coming back this way. If I had e to any function of x, the chain rule says that the derivative will be e to that function, but multiplied by the derivative of the function. So if we ever happen to have a situation presenting itself where we have a derivative of a function and e to the f of x there like that, we're just going to get e to the f of x plus our c. We'll do some examples. A lot of people, when you do these sorts of ones, they say, well, where did the 2x go? Or where did the 3x squared go, or whatever. It's not disappearing. There's a reason why we don't write it here, because it will come back out when we differentiate back again. Let me show you with some examples and hopefully it'll make a bit more sense. All right, so we have our integral of e to the x plus e to the negative x. As with any derivatives and integrals, a sum or difference is perfectly fine just to do each bit. Integral of e to the x is e to the x. Integral of e to the negative x is going to be e to the negative x divided by -1, isn't it? So we'll end up with just a minus out the front there. You can do that in 2 steps if you need to. Just checking, going back the other way, derivative of e to the x is e to the x. Derivative of e to the negative x is e to the negative x times -1, which then cancels out that negative and we get back where we started. All right, this one here, okay. E to the 4x, we're going to get e to the 4x, but we're going to get 1/4 of that to counteract for the fact that the derivative of 4x is 4. Derivative of x is x squared on 2 plus our c. Now this one here, we have this function squared. Now if we happened to have the derivative of this or some constant times the derivative of this out the front, we could go that way, but we don't. So the best way to proceed here, in fact, the only way really to proceed here will be to expand this out first. So we're going to get e to the 3x squared, which is e to the 6x, plus 2 times that, so plus 12 e to the 3x, plus our 6 squared, which is 36. Then we can integrate each bit. So we'll get e to the 6x, but we'll get 1/6 of it. E to the 3x will get divided by 3, so we'll get plus 4 e to the 3x. You can do that in 2 steps if you need to, plus our 36x plus our c. Next one here, clearly it would make sense to expand before we try to do any integration. E to the 2x times e to the 2x, if you're multiplying powers with the same base, you add the indices, so that's e to the 4x. E to the 2x times e to the negative 2x is e to the 0, which is 1. So we get e to the 4x, but we get 1/4 of it. You can either write the 1/4 out the front or put it over 4 there, it doesn't matter. And that one is done. All right, this page I've got 2 normal ones and a challenge one. Let's have a look at this here. We've got e raised to the function x squared plus 3. What is the derivative of x squared plus 3? The derivative of x squared plus 3 is 2x. So by recognising the fact that we've got our f of x there and our f dash x there, we can just go straight to saying this is e to the x squared plus 3 plus our c. Why? Well, let's go back the other way. If I told you to differentiate that, you'd get e to the that multiplied by the derivative of that inner function, which is 2x. And there you go. So it hasn't disappeared, it really is there. Let's have a look at this one. Same sort of situation. We've got this function here is like our f of x. What's the derivative of that? Derivative of that is 3x squared plus 4. Lo and behold, we happen to have that exact thing multiplying out the front. So we can go straight to e to the x cubed plus 4x minus 7 plus our c for our integral. If you're not sure about whether you're correct or not, differentiate back again and check if you get back where you started. Let's have a look at this one. This one is a little bit of a challenge. The reason why it's a bit of a challenge is because what I'm hoping that you will be able to do is to recognise something kind of cool here. Let's have a look here. E to the natural log of x. What does that mean? It means e to the log of x to base e. What is that? That is just x. You are performing inverse operations. So what this actually is the integral of 1 on x times just x. 1 on x times x is 1. Integral of 1 is nice and easy. And Bob's your uncle. All right? Be on the lookout for things like that. Inverse functions, you end up back with your x. Makes your life a lot easier if you can recognise those sorts of things.